change, maybe it is feasible or not. That is also important. So to consider a fluid mechanics problem, it is completely based on the physical scenario. After that physical scenario, we have to be analyze the physics of that problem. If this problem represents something, and if we change something, then these are the major effects with respect to the original things. So then we have a two things idea, fluid scenario and then physics, then we can use the mathematics. And we know that the scenario and physics will give to the Navier-Stokes equation plus some body force. Then we have to be added something new in the problem, because already Navier-Stokes equation is general equations. Then we have to be add something new in the governing equation. Then we will get a very nice model for our considered problem. Now the problem definitely is only in a Navier-Stokes equation. Then we apply some help of the numerical methods. Then discretize the problem. Then problems will give convert in the particular grid size. The grid, and this is very important lesson to the for fluid mechanics. If we develop the grids, we have to be an idea that how much grids are required to solve a problems, because one grid to another grid, the fluid is passing from the one place to another place. So that is also important feature for the numerical simulation. Then I have to be converted in the programming language with the help of the computer programming, and then take the very good computers and conduct a very good nice simulations, and after simulation we will get some results. Then connect that result with respect to the considered physics. If it is okay, then we can solve the problem. If our results are not going to match with respect to the considered physics, then definitely we have done something wrong. So that is one of the great scenario for a CFD problems, because it needs the several efforts, selection problem to analysis of the problem after the results we are getting. That is not a mandatory that we are getting the correct results, because sometimes mistakes, maybe our concerned physics is not good. Maybe we have dropped some assumptions, original things, or sometimes is the numerical problems, because most of those are doing the CFD, they are suffering with respect to the numerical simulations, because numerical simulations need the several efforts and several high frequency computers also. So that is a complete things with respect to the modeling part in the computational fluid dynamics problems. So basically I am going to discuss one of the interesting part in the CFD, that is called to the hydrodynamic stability analysis. How to analyze the stability for a given flow. Suppose there are several branches of the fluid mechanics in which someone are examining the flow features, someone is examining the velocity and other density pressure distributions. But my talk is developed mathematically how to analyze the instability in the flow. Those are the major cause to developing the different features in the different applications. So basically I will start with the laminar flow. So laminar flow is just, we see that this is one of the practical example in our house, the tap water. If you give a small strain to the tap, then flow is going to very smooth. That situation is known as to the laminar situations. And if to increase the strength of the tap, then we will get this type of situation, and the path of the fluid particles is going to be the disturbed. And path of the fluid particle of going to be the disturbed, then we will see that is the called to the turbulent flow. And you see that this is one of the another example, practical example. This is cigarette that is called to the up to here is going to the uniform path, and after that path it is going to the turbulent way, different ways. So basically laminar flow is nothing but a flow is going to a systematic path. There the layers of the fluids are not going to be the cross each other, but in turbulent case the layers of the fluids are going to be the cross to each other. That is called to the turbulent flow. Now actually the laminar flow is easy to simulate, but the turbulent flow is difficult to analyze because you need the several efforts. But in practically most of the applications are related to the turbulent. And turbulent flow not means that it is always dangerous, but it helps to other places also. Like as if a pilot is going with respect to when a plane is going, Airbus is moving, then the pilot always needs the laminar situations. If it is turbulent, then it is very difficult to manage the path of the aeroplane. So sometimes, but in same times, if you asking in the washing machine, if flow is going to the laminar in the washing machine, we will not get the correct correctness in the cleaning. So that means here we need to the turbulent flow. So we need the high drag and high mixing that time. Similarly, in the oceans, when we will see the cyclones, cyclones is developing the turbulent structure and the vortex are going to be destroyed. That situations is called to the turbulent situations. Now I comes to the general basic definitions of the stability. If you're talking about the stability means that something is there. Later I will comes to the fluid mechanics. First I will explain the very simple way what is a stability. Stability means if something, some objects or something is here, then my object is this, I put a disturbance. Then after putting the disturbance, I want to see the scenario. The scenario is this, if suppose something is the ball is here, I put a little bit disturbance. Then disturbance, then we see that now it remains the same position or not. If the situation is this type of this, you put the disturbance, definitely it will not comes to this place. But in this case, if put the slightly disturbance, then it will remain the same position. So that situation is called to the unstable situations, and that situation is called to the stable situations. Now another one is the neutral stable situations. Neutral means that means we position will change, but it remains looks same. So that is the kinetic energy is going to be the zero actually. That situation that is called to the neutral situations. Now the fourth one is very interesting. The fourth one, this ball is here. Now it's choice if you introduce the disturbance here, then definitely this ball will comes to here or either here. That maybe go downward and unstable, or if disturbance put here, then it remains here. Then two situation will create. So that means that it depends on the strength of our disturbance. If disturbance is good amount, then we will put the ball will comes to here and go to the downward. If disturbance is very low magnitude, then this remains to here. So basically, this is part of the nonlinear stability analysis. When we are going to discuss this part in this lecture also, see how to develop a nonlinear stability analysis with respect to the given flow. So basically, in the 19th century, Reynolds has observed this type of things. When he had taken a pipe, and in that pipe he has injected a dye, and he's seen the three different type of the pattern. One is the pattern is going to the middle part of the pipe is a very smooth manner. That is called to the flow is laminar. After that, we see that a different. This is original experiment. This is original experiment conducted by the Reynolds, and he has seen that after some time this zigzag type of patterns is coming, and another one is the after some time it will go to like that. So he have observed the three different type of patterns, and he had denoted like I say, first pattern is the laminar flow where the mixing is not possible, and second pattern the mixing is started, and that is called the transitional state or intermediate state velocity, and third one is the completely go a different pictures or different flow feature, that is called to the turbulent situations actually. So after that this Reynolds experiment, then this branch is completely developed that every flow have some type of the instability. So how to analyze the predict of instability? First is the agar we possible, then we conduct the experiment. If not possible, then we have to be conduct a computation and theory. What is the effect of the initial disturbance on the laminar flow? We already have given a one example here. I have key is strength or initial disturbance. Strength of the disturbance will depends on the stability in the flow. Either it is a low amount of magnitude or a higher amount of magnitude disturbance. It depends on the situations. Third one is basically those are doing the fluid mechanics. This is one of the key parameter. Reynolds number basically is nothing but is related to the velocity. If Reynolds number is going to be the increase, that means we are going to be increase the velocity in the flow, and that also depend in the situation of the instability. Now that magnitude of the disturbance, it is finite or infinitely small quantity. So these things, and another one now we are going to use the theory, how to develop all those things to analyze by the theory. That I am going to discuss the linear stability theory. So basically, mathematically, two situations are possible. When you introduce a disturbance, the response of the laminar flow to the disturbance is either in a small or in a moderate amplitude. Moderate amplitude means there is a finite amplitude of that. Amplitude is nothing but the part of the disturbance actually. So stable situation, if you implemented in the disturbance on the original flow, then we will say that is it remain in the original laminar state, that is called to the stable situation. Another one, if it is disturbance is growing, is the increasing and causes to laminar flow change to some another state, that is called to the turbulent flow. That is situation is called to the unstable situations. So basically in the hydrodynamic stability analysis, we have to be developed, or we are going to develop just a instability mechanism with respect to the given flow. There are some theories. That theories is the first one is the linear stability theory, and that will give you a good information about the flow feature. Then in the linear stability analysis, we have to be remove the nonlinear terms under certain conditions. Then we again we consider these some interactions, and that interactions comes to under the category of the weakly nonlinear stability analysis or finite amplitude analysis. And last one is a more complicated LES, large ED simulations and direct numerical simulations. These are basically complete simulations of a fluid mechanics problem through numerical. It needs several efforts with respect to the numerical analysis, as well as we have to be also know the computer efficiency or computer programmings. Otherwise, it's very difficult to tackle by the direct numerical simulations. So now I'm going to discuss few very simple practical examples of the instability mechanism in day-to-day life. First one is the Rayleigh-Bénard convections. Rayleigh-Bénard convections is every day we are seeing in our house. Just when you are going to boil a water, then we see that there are the small rolls in the bottom of the bowl. That roll is called the Bénard cells, and that cell appears due to hot water is coming upward direction. That means those waters are hot, particles are hot, then density will be reduced, and the lower density fluid comes to forward directions, and the higher density fluid go to the below directions. That rolls are developed, that situations. And this is a pattern, is a particular pattern that is called to the Bénard pattern or Bénard cells, and that type of instability is called to the Rayleigh-Bénard instability or Rayleigh-Bénard convections. So when we boiling the water, we always see this type of patterns. Another is the Kelvin-Holmos instability. That instability we can see in the atmosphere. Then two different velocity fluids come in the touch each other, then we see this nice structure in the atmosphere, and that is recognized by the Kelvin and Holmos, and that is known as a Kelvin-Holmos instability. Another one is the Rayleigh-Taylor instability. Rayleigh-Taylor instability is developed with respect to two different fluids with respect to two different densities. If suppose a higher density fluid, one is a low density, we are going to mix up, then we see the different type of pattern at the interface, and that interface is called to the Rayleigh-Taylor instability. Sometimes it's rotating systems. Those are the filtrations and metallurgy department. They are using the most of the systems are the rotating systems. And rotating system, we can see the centrifugal forces are developing the instability, that is called to the centrifugal instability. Suppose your system have a temperature with respect to, suppose you have a consider a channel, then there is a temperature, then instability is developed with respect to the temperature. So these are the few examples I have given here. Even apart from these examples, we have another different type of name instability like elliptic, hyperbolic, and based on your problems, we instabilities are developed. So I have taken a one test problem, and with respect to that test problem, in this lecture we are going to develop the linear stability equations, and another is a non-linear stability analysis part. So first to develop analyze for a problems to stability analysis, we need a basic flow. And when we are going to start the problem in any area, any area with respect to the fluid mechanics, then we first need the basic flow. And basic flow depends on the situations. Once you know the basic flow, that too now is the work to start the stability analysis. If you have a basic flow, that means basic flow is nothing but that is a flow features. The basic flow, then we have to be develop the first linear stability analysis, then finite amplitude or weakly non-linear stability analysis, then transition turbulence. Basically, these two steps are very complicated with respect to the analysis and with respect to the numerical simulations. So that's why I have developed the equation up to the weakly non-linear stability analysis. So we have to first take the basic flow, then apply the disturbance, then use this linear stability theory, then see the features of the instability mechanism. Then if we are able to capture the reality, then it's okay. If you have some problems with respect to the original flow feature, then we have to come with a new another approach that is called to the finite amplitude analysis or weakly non-linear stability analysis. And these three parts are basically based on the complete mathematics. When we use the detailed mathematics with the help of the theory of OD as well as the basic concept of the hydrodynamic stability analysis, then we can develop these equations in very systematic manner. We can develop and analyze the flow. So I have taken a channel problem. Before to explain the problem, I will just give a mathematical perspective of the stability. Suppose here V is denoted the velocity, P is the pressure, and this is epsilon delta definition in the stability analysis. Suppose some velocity, V is original velocity and B is the basic flow, that is the whole quantity is called to the disturbance. So this disturbance is initially some less than delta. This whole difference is the disturbance known as a disturbance. Initially t equal to 0, then it is a delta, some amount. Delta is a fixed quantity, positive quantity. And after some time t, here is I replace 0 by t, then we see that it remains, again a small quantity epsilon. So there is a relation. This epsilon is depends on the delta is depends on the epsilon. So that means this disturbance remains in particular band. It will not going to be the grow. If suppose initially is a delta and it is going to epsilon is too much large or greater than delta, suppose, then it is, we can say the flow is unstable mathematically. But it remains in a particular band that we can say the flow is going to be the stable. So that is a mathematical perspective, and defining a basic flow is stable or not. B stands, capital B stands for the basic flow. Small b is the normal velocity, just a velocity in the part. Then difference between these two is called to the disturbance, and disturbance is going to be the finite, that in all time for t greater than equal to 0, then flow is said to be the stable. Otherwise unstable situations. When same definitions we have to be converted in the picturizations. Same definitions, same mathematical definitions, we have to be converted. This is your basic flow. I will also explain how to develop a basic flow, but this basic flow, and we have given a disturbance here. Then I'm now see the picture, this disturbance remain inside the basic flow or just growing. That is the main feature for this instability. If it is remains and sustains a particular band disturbance, that is called to the stable situations. But if it is growing and magnified, that is called to the unstable situations. Most of cases in the hydrodynamic stability, we generally use to the wave packet form disturbance. That means periodic disturbance. There is another part of the mathematics how to we tackle the periodic disturbance. And basically this periodic disturbance will comes to help with respect to Laplace and Fourier series and Fourier transformations. So based on that theory, we use to the periodic disturbance for the here I use the periodic disturbance for the stability analysis. So this is a whole procedure mathematically. This is very interesting. First, this is a velocity part which is decomposed two parts. First is the basic flow. So just I writing here few things. Yeah. So this part is a basic flow. Once I know, if I know the basic flow, then I use to the disturbance. This part is a disturbance. So then in the stability analysis, when we are going to start the basic plus disturbance. Now original U is replaced by these two quantity in the main governing equations, and that disturbance is periodic form. This is the periodic structure. Now we see here is nothing but e raised to power iota alpha x, one thing, e raised to power iota beta x, beta z, one thing, and e raised to power iota alpha c is nothing but cr plus iota ci. Here I have written the complex wave speed cr t. I will analyze these terms. So this disturbance is given in the periodic forms. Now two type of analysis are going in the linear stability analysis. One is the temporal stability analysis and spatial stability analysis. When alpha and beta are the real numbers, then it is called to the temporal stability analysis. If alpha and beta are the complex number and c is the real number, then it is called a spatial stability analysis. For most of the stability analysis cases, generally our interest with respect to the only the temporal stability analysis. That's why, because temporal stability analysis gives us several informations. So that wise most of cases we are going to be used to the temporal stability analysis. Now see this picture. If you understand this one, then complete scenario will be clear in the stability analysis. This quantity will go to the finite. Because iota alpha x, this is nothing but cos x plus iota cos alpha x plus iota sine alpha x, and the modulus of this quantity will go to the finite quantity. This will be also finite. Only then we iota is multiplied by iota cr, then this term will give to the two term e raised to power iota alpha cr and e raised to power, this is minus ci, this is ci. CR and CI. C is replaced by the complex CR and CI. CI T. This. See, this is again a finite quantity, but only that this is a depends on the sign of CI. This quantity e raised to power 1 minus is the outside, the minus is plus. This is minus. So CI T whole expressions. In this whole expressions, we are obtaining e raised to power CIT. This CI sign, if greater than 0, then we see that this term is going to be the infinity. If CI is less than 0, then it's going to be the 0. And CI equal to 0, that is a fixed quantity 1. Three cases is possible: Ci greater than 0, Ci less than 0, and Ci equal to 0. In these three cases, will decide the stable, unstable situations. The whole expressions, in this whole expressions, only the part of C that is called to the Ci will decide the stability in the flow. So sign of the Ci will we have to be take care. If sign of the Ci is greater than 0 or less than 0, then we can say that flow is stable or unstable situations. So this is the complete discussion with respect to the mathematics, that mathematics will always give to the very clear cut picture. Only this expressions is going to be the finite when Ci is less than 0, otherwise no. If Ci is greater than 0, this amplify, this is nothing but this is a disturbance. Disturbance is going to the amplify, and that flow is going to be unstable. So that is a complete picture. Now, after the putting all those things, we will get a very nice picture. I will show you how to develop Ax equal to Cbx. This is the Ax equal to Bs is called to the generalized eigenvalue problem, where C is nothing but eigenvalue. The same C, this same C, where C is the eigenvalue, that C is C equal to Cr plus iota Ci. We have already seen from equation 3, only our interest is the, sorry, this is Ci. Only Ci. Our interest is Ci. That's why I have written here Ci is less than 0 is stable, and Ci greater than 0 equal to 0 is neutral stable, and Ci greater than 0 is the unstable situations. So this is the complete picture. When we are going through complete problems, so we have several non-dimensionalized parameter. Here is the parameter PR is represent the type of fluids. R is the when we have considering the temperature in the flow equation, that is called to the buoyancy effect, and another is R is the strength of the flow, in which we have to pick up the minimum point in the domain where is the flow is unstable by a particular point, and after that flow is remains unstable. So these are the called to the criticality conditions for a stability analysis, but they will use to the later once you know the stable or unstable situations. The same time CI have a CR. If that CR is not equal to 0, that is situation is called to the oscillatory growing modes. And for same CI, if we see the corresponding CR, then it is equal to 0, that is called to the stationary mode case. So this is the some analysis point of view, we have to be captured this type. This is oscillatory mode, this is one is the stationary mode. So now comes to this theory, then what is theory says that when we apply the linear stability analysis, so when we apply to the linear stability analysis, then we have see the several situations. Situations means the part originally the things are going to happen like that. See, reason is 1, 2, 3, 4 is nothing but C is the eigenvalue. In generally later on I will call to the just eigenvalue is nothing eigenvalue, that's called to the modes. We are calling in the fluid mechanics modes. So these are the modes. If all our modes are decaying means going to be the 0, then disturbance is going to be 0, then flow is remains the stable. That situation is part. But suppose few modes are growing but still decaying in the time space. Few are growing but in after some times they are decaying. That is situation is this. Third one is the conditional regions. Maybe few modes are decaying and some one of the modes are growing. Out of the several modes, several eigenvalues is Ci greater than 0. That situation is comes to in the category conditional stability. But is last one part, if there is a one positive mode, then flow is unstable. So basically, linear stability analysis gives a very interesting things that once your flow is unstable, the beyond that always is unstable. Before the linear stability, we don't know. We don't know means the flow is stable or unstable, but at a critical point of the through linear stability, we can declare that the flow beyond that point is unstable. So it always give to the instability point, not the stability points. Sorry. So these are the example where the linear stability critical point is considered is here in the pipe case, we are not calculated the pi, not able to calculate. That means infinity always showing the linear stability analysis is stable. Channel flow is due to the pipe 772, but actually this flow is unstable beyond 1000. And moving balls in case is always due to the stable, but actually flow is going to be unstable in the Reynolds number 360. So, but one is interesting thing in the linear stability. Once you know the 5772, then you are clear picture give to the linear stability. After that number is flow definitely unstable. Whatever analysis you have to be implement, either experimental or another weakly nonlinear DNS, anything, definitely flow is going to be unstable after that point. But before that point, flow is stable or not, we don't know. So that for that we have to use the another analysis. So I have taken a very nice channel problems, and here I have used the one body force that is called to the temperature conditions. The temperature conditions I have taken in the channel based on the physical scenario. I have seen this governing equations for this problem. So every problem have a governing equations, and this comes to this forcing factor. It comes to this is comes with respect to the temperature. And this is the temperature equations, and this is a diffusion part in the temperature equations, and this is the advections. Advections means that means flow with carrying with respect to the temperature also. And when we are doing the fluid mechanics, we have to need some non-dimensionalized parameter, because to explain the physics of the problem, we easy to explain with respect to the non-dimensionalized parameter, because non-dimensionalized parameter going to represent something like as a Rayleigh number. That means the heating in the systems, it is going to be represented by the Rayleigh number. Reynolds number is strength in the flow, that means a magnitude of the velocity, and PR is the Prandtl number, that is also denote the type of the fluid. Generally we are calling a PR equal to 7, that is a water case, and PR equal to 0.7, that is called to the air case, and if PR equal to 70, then we can see the heavy oils case. So we taken this type of governing model. Then we first, this is a vector form equations. We open these equations, and these three equations are the Navier-Stokes equations. And another one is the temperature equation. This one is the continuity equations. For a channel problems, I am going to develop the equations for the linear stability analysis. So first I need the basic flow. So for a channel problem, I already told when we are going to start the stability analysis, then we need the basic flow. So this is a basic flow. First, in the channel problem, I have a few assumptions for that problem, even though it is analyzed by me also their channel problem. So that the assumptions are realistic, not I have taken arbitrary. So the flow I have taken the steady, that means it is independent with respect to the time. Unidirectional, the channel always is going to be the two-dimensionally, the one direction flow, other direction is zero. And fully developed, initially there is no flow is the fully developed. After some times we see the say velocity at that here, velocity at this point, and this point, always same. So that situation is known to the fully developed situation. A flow is invariant in the flow directions with respect to the velocity, that is called to the fully developed. So after these assumptions, we use these assumptions here. Suppose two-dimensional case, then two-dimensional case, this term will not come. Those are W terms are coming, they will not come. This equation will not come. And two-dimensionally case, then we have to be drop this third component, only this. Now unidirectional flow, that means V equal to 0 and U equal to not 0. So if V equal to 0, the change in the velocity is, if there is no velocity in the V directions, then the change in the velocity is also 0. If we don't have a velocity, then how is it possible to change? So that is also 0. Now the term will comes to del U by del X, and del U by del X is give to the U is a function of purely Y. U is function of purely Y. So that is a way. So now U is a purely function of Y, then this del U by del X is, this is 0, steady state, that is 0, then V already 0, that is gone. Only the term, this is U is only function of Y, so only this term is gone, this is remain. This is remain and this is remain. Similarly, we have to apply that concept for these other equations, because there is no V velocity, then we remove that one. Then this is time free from the time, that is removed. V is not there, then we have to be removed. So del P upon del Y equal to 0. The second part is comes to del P upon del Y equal to 0. Here the first part is this term plus this plus del P by del X. One side P is a purely function of X, and another side the purely function of X is quantity is the equal to purely function of Y. That means the pressure gradient is going to be the constant, only the one options. So based on this, I remove all the constants, my assumptions, and I will get the final this type of equations. This operator used for something else, but I will get this type of equations, and that is called to the basic flow. This is my basic flow for a channel problem, for a heated channel under the certain heating conditions. So now I want to analyze the stability of this basic flow. That means we solve these equations, we have to be calculate basic variable is denoted by the U naught and theta naught quantity. So these two quantity if known to us, then we have to be comes to next step to develop the linear stability analysis. So first part is the developing of the basic flow. Now basic flow, when we analyze the basic flow, these are the basic flow features, and basically it's give in the for a channel problem, it gives to the some structure, and that structure give to the point of inflections is appear in the basic flow velocity profile, then it is one of the predictions that the instabilities are available in the flow, but it's not mandatory, because this statement is generally useful for the inviscid theory, but in viscid theory, viscous fluid also, we can see this type instability inflection points comes into the basic flow. That inflection points will give to a instability in the flow. Inflection point is nothing but when concavity is going to be the change. Here is the concavity this side, here is the concavity this side, then with the second order derivative is going to be the 0. That is the flow heavy. Here is the same thing, this side concavity and this side. Upward and upward concave and below concave. So that is called give a inflection point. And that inflection point helps to give to the idea that key flow heavy instability. So now comes to the linear stability. Linear stability we comes to the basic plus disturbance. Disturbance is given in all directions with respect to time also. So we have to be used because disturbance is given only by one direction. Oh, basic flow is in one direction, unidirectional, that is called. Another direction is there is no basic flow, that we have taken this type of structure. So after we substitute these equations, this first one equations for each field variable, then we will have this type of relations. You suppose this one particular term u dash del u, then u is replaced by u naught by u dash, and derivative of this we already know that this is a purely function of y. That's when we take the derivative, this will go to the 0, and u dash is a function of x y z t, then it will comes to the this state. Now when we multiply this, then we will get the two term. This is u naught is known to us, this is a linear term. This is a linear term, but this is a non-linear term. And this non-linear term we have to be removed for a linear stability analysis. So we have to be analyze all terms like such a way and remove the non-linear term, we will get a linear disturbance equations. That is called to the linear disturbance equations. But your genuine questions, if you are going to remove the non-linearity everywhere, then actually it will give to the original things for a problem. That is a matter. But that matter answer will comes after we analyze complete problem, then we can say that it gives something, otherwise something is remains. So basically this non-linear order, this order of this term is very less. Why? Because the disturbance is very small. The infinitely small disturbance we have given, the magnitude of the disturbance is very less, then product of the very less two quantities again to the very less. If suppose this quantity is less than 1, u dash is less than 1, then product of the u and del u by del dash is the less than 1. So it is very small quantity. That's why I have dropped here, because our theory says that we have choose the very small amount of the disturbance. So now after removing these terms, we will approach to the, this is called to the, we remove it, or we have taken only the linear term. That linear terms is calling to the linear disturbance equations. And the whole procedure is known to the normal mode analysis. And this normal mode analysis means that we have capturing the oscillations. Because normal, if those are doing the differential equations, they already know normal modes means the oscillations. That means a wavy form disturbance we have used here, and that's why it's called to the normal mode analysis. So now comes to the this linear disturbance equations. Now you use to the this disturbance part like that, e raised to power I alpha x. I already analyzed these things when only the term Ci is responsible. In the previously I have discussed, then Ci is greater than 0 or less than 0 is depends the stable or unstable situations. So once you put all these expressions in this expression 31, we put in this, then we will get a this type of equations. And generally these equation is known to the linear disturbance equation for here is it is a channel problem, but for any problems you can develop this type of the linear differential linear disturbance equations. But in this case channel we obtain the ordinary differential equation, all are the coupled, and but it's not necessary always the basic flow is the unidirectional. No, If suppose you have a biomedical problems, you have a some arterial problems or biological side, always you will get the two-dimensional and time dependent. The basic flow, it not necessarily always is the unidirectional. Basic flow, one direction, two direction, and three direction is steady or unsteady. So it depends on the characteristic of the basic flow. After basic flow, the procedure will go to the same way, except this. Here I have used the u not equal to y. But if suppose basic flow is the two-dimensional x and y, then I will use the u not equal to x comma y. So that is the concept to taken the basic flow. And after basic flow, then we use to this type of periodic disturbance, and then we will get this type of differential equation. Here in the case of disturbance because of ordinary like as because we have a one-dimensional basic flow. Now see this term here, only the term c will come. In each equation we will get this term. This will comes to because of this del u by del t. Del u by del t. U dash is a disturbance, or when u dash is nothing but e raised to power I to alpha x beta z minus this one. If you take the u here, then you will get this one. So this term is we take the one side, remaining terms we take the one side. So basically those are c is nothing but is eigenvalue. C is we are treating like as a eigenvalue. So these terms comes to one side, other terms comes to the one side. One more interesting things in the fluid mechanics, those are using pressure is always there. When we are going to solve the pressure, the several difficulties will come to the solution of the problem numerically. So better to avoid this type of difficulty, we have to eliminate the pressure. That is one of the interesting way to tackle a problem in a systematic way. So when we take the cross multiplication of these equations with respect to the P, then we will eliminate the pressure. And after elimination of the pressure, we will get a nice set of equations, this fourth order set of equations. Because of this fourth order only based on the elimination of the process, nothing else. Now this is a one part of the fluid mechanics that we have developed. Now second part, the solution. Because we know these equations not easy to solve by analytically. Even though these are the ordinary, but the equation are coupled and several terms are there, then to capture by analytically is very difficult job. So we have to be solved numerically. It depends on you which one methods you are going to be the implement, but I have used the method which is called to the spectral collocation method, which is a more accurate method, and equations are going to be discretized at the Gauss-Lobata collocation point. These a particular type, those are not able to know the collocation method and they are able to know the finite element method. They can discretize the problem with respect to the finite element method or in Galerkin methods. Whatever methods you are going to be comfort, then used to here to discretize these equations. But this stability analysis needs the several amount of the grids. That is an important feature. Once you discretize this problem, here I just going to little bit explanation of the numerical method because I have used the spectral collocation method, and these are the collocation point. Basically, these collocation points are clustered near to the boundary, and these are sparse to the middle part, and this is the representation of these collocations. And these are not uniforms in the problem because the distance of this collocation to this collocation is something else, and this collocation to this collocation is something else. So these Gauss-Lobata collocations are not the uniform collocation point. You may use the uniform also, it doesn't matter. But here the one particular type of the collocation points I have used in my research, and basically approximation functions are Chebyshev polynomials. So based on Chebyshev polynomial and Gauss-Lobata collocation point, and we have developed a differentiation matrix dj, and I hope those are doing the numerical simulations not worried about this method. Is very easy. If you are not able to understand the theory of this Gauss-Lobata and Chebyshev collocation method, you may concentrate on this derivative, or the property of this derivative is this: we have to replace a derivative by this matrix. This is a matrix. When we convert in the form, this is a matrix n cross n. If n collocation point, then matrix will comes to n plus 1 into n plus 1. So we have to be replace a derivative by this differentiations. And after the derivative are going to be replaced, if suppose your second order derivative, then we multiply 2 times this differentiation matrix. If the third order derivative, then we multiply the 3 times, and fourth order you may multiply fourth order, but like when we are going to multiply the continuously, then error propagation is going to be the increase. So sometimes we need to the attention with respect to the another numerical parts, how to tackle a problem the numerically. So after this, we will get a eigenvalue problems. Basically, all linear stability problems are going to form a eigenvalue problems. That is, eigenvalue problems is generalized eigenvalue problems. So we come up to a generalized eigenvalue problems through the linear stability analysis, and that linear stability analysis give a representation to now analyze, because I already declared that our interest the sign of this C, sign of Ci, imaginary part of the eigenvalue C. Because in the previously we have seen, because our disturbance is given by iota alpha x plus beta z minus alpha ct. This term, only the one part Ci is responsible for the stable or unstable situation, that is Ci is greater than 0 and Ci is less than 0 or Ci equal to 0. So always when we are going to take a problem, and problems we have to be develop the linear stability theory equation, and equation will forms a generalized eigenvalue problem, and we have to be concentrate only the eigenvalue C, the imaginary part. So now we see how to calculate. Suppose first to calculate the eigenvalue, because if Ax equal to Cbx we have obtained, then several platforms available to solve the eigenvalue problems. If you are going to MATLAB, then MATLAB will directly give to the eigenvalues. If A matrix, B matrix are ready, then we can directly put a command eig a comma b, and then we will get the all eigenvalues. So my question is this: if you suppose C is the eigenvalue, set of the eigenvalue. Suppose this is 50 by 50 matrix, then 50 eigenvalues you will get it, column 50 into 1. Then eigenvalue C1, C50. And these eigenvalue is complex. C1 plus iota C1R, C1I. But my interest only the Ci. So we see the sign of, for each eigenvalue, the sign of the Ci. That is the interesting things. Suppose you have the 50 eigenvalue, 30 eigenvalue have a Ci sign is negative. 30 eigenvalues Ci sign is negative. And 20 eigenvalues is Ci is greater than 0. Is total out of 50, 30 is the less than 0, and out of 20 is the greater than 0. Then 30 eigenvalue, if Ci is less than 0, flow is going to be the stable. We don't think about this. If Ci is less than 0, we not concerned about this. Only that we will see that which one eigenvalues have a imaginary part greater than 0. These is 20 eigenvalues. Now we arrange this 20 eigenvalue. Which one have a most dominating? Dominating means most higher value. Suppose one Ci is 1, 1 is 2, then we descending order we have to be arranged it. And the most unstable, first one most unstable, most largest value of the Ci is called to the most unstable mode. And we concern always in the linear stability analysis most unstable mode. So that most unstable mode we pick up. That unstable mode we have to be pick up, and that is called to the most unstable mode, that is growing modes. So case first is calculate eigenvalue, examine the real and imaginary part of the eigenvalue. Third one is determine the most unstable eigenvalue, Ci is greater than 0. Then other, now with respect to that most unstable, Cr is equal to 0 or not. That is also important. CR equal to 0 or not. If it is 0, then we can say that directly we can declare that is stationary mode. If it is not 0, then we can say that this is a growing or a oscillatory mode. So to the one type of analysis we have conducted here, second type of analysis we have to be conducted here. Further we have to be analyze a growth rate. Growth rate is nothing but alpha into Ci is known as a growth rate. So alpha wave number is fixed. Ci we have to be obtained already. The whatever value we have obtained, that we have obtained a growth rate at a particular point. If growth rate is positive, then we can say flow is unstable. If growth rate is negative, then we can say that a flow is stable situation. Fourth one analysis, we have to be analyze critical parameters. Suppose you are varying the several parameters. So we have to be varying the several parameters. Then we have to be fix one parameter at a particular number. Then we see that we changing the other parameter, what happened. Then you see that we changing some parameter, then flow is stable, sometime unstable. Then after between these points, we have to be provide a one fine point. At that value of the parameter, the flow is going to be unstable situations. So basically always we will talk unstable situation in the linear stability analysis. Fourth one is the kinetic energy in the flow. This is another part of the analysis for the linear stability. Kinetic energy means that is going to be the zero at the linear stability point. And that analysis always confirm us to that key linear stability analysis through eigenvalue problem is correct or not. So kinetic energy at a neutral stability analysis, it should be go to zero. If it is not zero, then we have to say that our linear stability analysis is not correct. And last one is the flow features. We have to be see the what happened with respect to the flow features, that we can call to the secondary flow analysis in the linear stability analysis under the case of this. So these are the basically few analysis. Those are doing the fluid mechanics. They can easily identify once the Ci is obtained. Here I have graphically shown. Once we have to calculate the critical point, so after the critical point we have declared the unstable situation beyond the stable situation. We not straightforward say the stable situation, we say that the flow is linearly stable. Below that point may be unstable, but beyond that point, this line, definitely whatever analysis you have to be implement, is flow is always going to be unstable. So according to the wave number with respect to Reynolds number, with respect to the Rayleigh number, we have to be develop this type of the boundaries. Now see the growth rate. Growth rate, I already informed that growth rate is nothing but alpha Ci, and if it is positive, then it is say the unstable part, and if it growth means disturbance is growing in particular, rate of the disturbance is growing. If rate of the disturbance is growing in the flow, then flow is going to be the unstable. That means all playing the disturbance is playing the major role. So that time if it is negative, then we can say that flow is a stable situation. So this is a parametric analysis. If parameter is going to be changed, what happened with respect to the instabilities. And the stream functions is the periodic nature of the flow feature, which show the in respect of that the flow patterns is going to be in the periodic forms or not. That is given, we have to be analyze the results, but these features basically need the good amount of the physics that we can analyze the results actually, because if without knowing the physics, be very difficult to analyze what they are going to be represent in the stability analysis. So basically I given a general idea if a growth rate is positive and negative, then what happens with respect to the instabilities. Now this is energy analysis, because I have not derived here, because this is a little bit derivations how to derive the energy equation. I just say that a disturbance quantity we have to be multiply with respect to the disturbance equations and take the average volume average. Volume average means particular cell, and that cell is domain. Domain is the suppose in channel that is comes to -1 to 1 or -L2 plus L, or wave number in respect is the 2 pi period we have taken. So that way things is the kinetic energy banners we have developed. But what is the objective of that? That is a very interesting part. If suppose the instabilities comes in the fluid mechanics, we have seen the Navier-Stokes equation, several terms are there. Here is the like as V dot del V plus some del V upon del rho equal to del square V, nu time 1 upon Re, just we can say that del square V minus del P and some another forcing factor. So based on this, which one term is more dominating in the flow? To capture a particular dominating terms in the mathematically for the instability, we use the kinetic energy balance. So that is terms is going to be with respect to the shear term. That is comes to the Rayleigh number, that means the density due to the temperature, that is called to the buoyancy instability, that is called to the due to the viscosity with the help of, and that is called to the dissipations. So that analysis helps to us and declare something ki this particular part is creating the problem in the flow. So we have to be analyze the particular part in the flow and we declare based on this type of instability. Suppose, but all terms will, some will go to the zero, because the kinetic energy at a critical point is going to be the zero. I will show some results which are calculated by me. So this C, this terms is sum of the each term is going to be zero, but most dominating term is this. That's why this instability is called to the thermal buoyant. TB means thermal buoyant. Then the case C here is also is the most dominating, this is called to the thermal buoyant. See here, this case. Here is the first term is more dominating, second is almost going to be the zero, and third is minus 1. Only the positive part we have to be see which one is dominating in case of the positive. So because positive is to disturbance is growing. So here is this one dominating, the first term ES is dominating, that is called to the shear instability. Sometimes two parts are sharing each other, that is called to the mixed mode type of the instability. That is the scenario to develop to the different type of instability mechanism in the flow. But basically this complete part is related to the physics. First, if you know the things, then we can go further beyond the energy analysis. But it's not a tough. It is a very systematic and very informal and give to the very nice information in the fluid instability mechanism, that which one part is creating the problems with respect to these parameters. So that is things. Now this is one of the part of the linear stability analysis. Now I comes to the next part of the weakly nonlinear stability analysis, or we can say the nonlinear stability analysis or finite amplitude analysis. So first interesting thing we have to know that why we need to the nonlinear stability analysis, because I already declared few drawback of the linear stability analysis, like as a channel flow. Like a channel flow, when we will go to the through linear stability analysis, the channel flow is always give to the linear stability critical point is 5772. But original experimental results is give to the flow is unstable on a Reynolds number 1000. I just again repeating, linear stability analysis give a point, beyond that, sorry, this is a point, beyond that point is flow is unstable. Whatever analysis you have to implement, but below that point, that side, we don't know, stable or unstable. But this, after this point, flow is unstable. So that is one of the successful result in the linear stability theory. If we have a point that beyond that point, we have a flow is unstable. So that is a major advantage, but we are beyond that, we are not able to say that flow is stable or unstable. That is a major drawback of the linear stability analysis. That is a one thing. Second, linear theory provides only the qualitative informations, not the quantity. We are not declare the strength of the amplitude and growth, magnitude or something. So we have to be do the qualitative, means we have to be declare the things with respect to the outputs in a physical scenario. But we have that things is a particular critical point is this, beyond that flow is unstable. That is very difficult to declare from the linear stability analysis. Third one is the exponentially growth, because we have taken e raised to power iota alpha ct. Last one is the growth rate. So this is going to be increased in the exponential way. It is going to be finite or not, because you see the in last picture I shown the growth rate is going to up to here, then it is decreasing. So that is okay. That is a stable situation is going to, but we don't know every time it will go to like that or go to like that. If it is going to like that, they're very difficult to predict the original things. So that is a few drawbacks in the linear stability analysis. but it gives the several informations. So we can conduct the for a problem the instability analysis. One successful results we can see it in the literature. Already I have declared onset of the instability. Second one is the Rayleigh-Bénard thermal convection. The linear stability analysis gives the critical point 1708. The same time experimental critical point is the 1705. It is very close to the experimental result. So not now always not give to the bad results linear stability analysis. It give very close to the linear stability experimental result. Taylor-Kiewit flow. Taylor-Kiewit flow basically flow between to the two concentric cylinders. That is called to the Taylor-Kiewit like this. This flow is called to the Taylor-Kiewit. Between the flow between the two cylinders, that is called to the Taylor-Kiewit flow. These Taylor-Kiewit flow is almost stability points are matching with respect to the experimental result, and experimental results give to the central figure instability. And same times we have observed through the linear stability analysis central figure instability. So these are the few successful study and few drawbacks in the linear stability analysis. But once we are going to be analyze the things in mathematical way, we will get the several information with respect to the linear stability analysis. Now I comes to the non-linear stability analysis. So basically, in this analysis, several authors have worked and but most recognized, even the Heisenberg is developed few very interesting things for the non-linear stability analysis. But in case of 1994, Landau have given a very nice theory to analyze the mathematical perspective of the linear stability and non-linear stability analysis. And this disturbance is nothing but original field variable minus basic state that are going to be converted with respect to the amplitude. And he has taken a very nice idea. He is saying that we are not going to do the whole non-linear analysis. We will see whatever what things happen with respect to the linear stability critical point. Suppose this is a linear stability critical point. He want to see the scenario in this neighborhood. What happen in this linear stability analysis critical point? What happen in the flow features? And that flow features are completely developed with theory of ODE, a concept of the theory of ODE. So physically, what does represent? He wants if he is going to in the neighborhood of the is going to be the neighborhood of this critical point. Landau has given a theory with respect to the neighborhood of this critical point. That means because linear stability is only the best most unstable mode, highest most unstable mode. He is saying that suppose in time space, most unstable mode is going to interact with respect to other modes and growing the disturbances continuously. And if disturbance is growing, then flow is going to be unstable. So very logical idea that most unstable mode becomes a dominant very soon, and is self interaction with respect to the other modes will generate the harmonics and distort the mean flow. That situations he has observed and say that we have to analyze the things about the linear stability point. So that is the way to capture by the Landau constant. So this is a theory. So we have to be use this is basic part and this is disturbance one part. We have added the another part and complex conjugate. In the previously linear stability analysis, we have taken this only up to here. Linear stability analysis we have taken up to here, but in the non-linear stability we have taken the other interaction plus complex conjugate. CC stands for the complex conjugate, and these terms are going to be represented in terms of the amplitudes. That beta t is amplitude, and he told me explain the things with respect to two different time scale. One is the linear stability time scale. He not disturb that time scale, and another one is here taken the slow time scales. That slow time scale and non-linear interactions he have captured and put this equation 53 on mean governing equations and 54 the two time scales, and he developed the different harmonic order equation. Basically, those are doing the fluid mechanics, they know how to develop the equations for the perturbations method. So the similar concept, almost similar, different order equations we have to be developed and solve the different ordering case and develop the different equations by the using the different harmonic interactions, And these are the little bit calculation is tricky, but basically those are doing the perturbations analysis in mathematics, there we can do it easily. So these equations will form a very interesting things is the Landau equations. That is the main core part of the nonlinear stability analysis. B is the amplitude that is converted in the physical amplitude these equations. Before explain these equations, I will explain something else because this is a particular equations. Now I give a one interesting result or interesting example. Suppose dx upon dt equal to ax minus bx cube. This I am writing. So now my question is how to say that a bifurcation analysis for this problem is a very completely mathematical theory, and bifurcations occurs in everywhere. Most of the problem is periodic and other problems. Bifurcation means a solution is going to be changed with respect to a small change in the parameter. If you change this parameter here, suppose a and b, if you change the small a in a, then solution is completely changed with respect to a different b. So that is called to the bifurcations. So bifurcation analysis, how to develop that, I explain the very simple equations dx by dt ax minus bx cube. It looks like same type of equations. So bifurcation analysis, we see the critical point. So critical point, this is f of xy. This part is called to the f of x. So f of x equal to 0, then we say that x equal to 0 and x equal to square root of a by b plus minus. How to develop a bifurcations for this type of equations? X equal to plus minus square root of a by b. So these are the critical points. Basically, in the fluid mechanics, these points is called to the basic flow points, say basic flow, xb and xd. So now we see the picture. We can now we first plot this picture. X dot is, we plot x dot is the dx by dt ax minus bx cube. We want to plot this graph. If we are going to plot this graph, you see, suppose a is greater than 0 case. Later I will come to these equations, because once you understand this equation, easily we can analyze this equation. If a is greater than 0, 100% sure b is greater than 0 for a real solution. Because square root a by b, then a by b is always positive when b is greater than 0. It is only the possibility. So this is scenario. Now we plot this ax minus bx cube is nothing but if a is greater than 0, so this is going to be like this. This and this and this. And this case, generally, if we say that the directions we are going to be defined like this. If we go to the negative directions, negative x and graph is negative, then we put the direction. Otherwise, it is positive, then reverse directions we are going. Here is the we going to the negative direction. Graph is negative, then direction is same. Here beyond that point, we go to the negative direction, but graph is positive, then opposite directions. Similarly, for this one is the positive directions and x is going to positive, graph is positive, then they are same directions. But if it is opposite, then we just this one. That is called to the sink type of situations. Both arrows are coming to this point. That both arrows are far away this point, and this is same. So this point is called to the stable point. And this is point is called to the unstable points. Generally, I am denoting the solid state part in the stable points, and this is to the unstable points. Same times, mathematics say that if you examine the f dash x, slope of that curve, if f dash x at a point xb, these are the xb points. These are the xb points. At xb is greater than 0, unstable. Unstable. If less than 0, then we can say that is stable situation. Now we check it. What is the f dash x? F dash x is nothing but is a minus 3bx square. We check for the x equal to 0. F dash 0 is a. We already declared a is greater than 0. Then if f dash x is greater than 0, then unstable point. This point is called to the unstable. 0 point is the unstable. See, the mathematically we are declared unstable. Here is the graphically we have declared unstable. 0 is unstable. Same if you apply the point f dash equal to square root over a by b. Both we can check the plus minus because square is there. Then we put here a minus 3b and a by b to cancel, then 3a, and that is nothing but minus 2a. A is positive, that means this whole quantity is negative. A is positive already declared, then this whole quantity is negative, that is called to the stable situation. We already declared these 2 points, x equal to minus root over ab and x equal to root over ab, both are positive. Both are stable, sorry. So these points are stable situations. So same things, first we have to be consider the critical point, that is called to the xb and x plus, these are take the critical point. At that critical point, the derivative f dash x is positive or negative. That will decide the stable or unstable point. So this is called to the bifurcation analysis for a ordinary differential equations. So that we are either, if you are not calculate the f dash, then we have to be go through the graphical. We have to be take the graph with respect to this graph is the with respect to x dot to x. Then we say that the arrow is coming to particular point towards both arrow, then it is called to the stable. One more is this. Suppose if you are not able to analyze the problem in the both these two methods, there is another one method is also possible. Dx by dt, sorry, ax minus bx cube. Then we take the potential of this system. Then vx is nothing but is just an integrate of this equation without constant. Then we will get a ax square by 2 minus bx4 by 4. If a and b are both are positive, then we plot this vx. Then we plot this vx is nothing but this is a vx. Then x square, sorry, we generally say that potential is negative, this negative sign with respect to this. Dx equal to dt equal to minus this, we have to be integrate with respect to minus sign, that we will get the potential. So the potential Vx is given by this, then we plot this one, then we will see that the plot of this Vx is like this. So sorry, this, see this point. Similarly, in the first definitions we have introduced, if point is here, then disturbance you have to be implement, then it is going to the unstable situations. So that means x equal to 0 point is unstable. If point is there and point is here, then it is called to the stable. So the several ways to declare the things in mathematics. The actual scenario, if point is stable, we comes to the potential way, we comes to the derivative way, or we comes to the picturizations in which one point is stable or unstable. So basically my objective to explain these equations is that looks like a very nice equations for the subcritical bifurcations, because generally in ordinary differential three fundamental type of bifurcations. One is the saddle node bifurcations, other one is the transcritical bifurcation, and third one is the supercritical and subcritical bifurcations. So basically this equation matching with respect to subcritical or supercritical equation bifurcations in the theory of ordinary. So this is looks a is nothing but 2a alpha ci, x is nothing but mod of a square, minus b, then we can change the minus 2a1 square is the b, and A4 is nothing but this AX cube. Then we can develop this X4 and convert, we can solve it, and then we can develop the bifurcations. And basically, when it comes to the bifurcations of this, similar these equations, then 2 points are the equilibrium points, are the stable equilibrium point, and 1 minute. See, comes to that situations. Even the velocity potential, I have developed this one. In the recently, I picture the potential functions graph is this. That point is unstable for a supercritical bifurcations. So basically, the analysis will decide the A1R. When you will go to this analysis, similar type, then A11 is a parameter where is greater than 0, then subcritical bifurcation, and generally we in fluid mechanics use the subcritical instability. Same things, if it is positive, then we can say that it is a I just told the reverse. If it is negative, then it is called to the supercritical bifurcations, and if it is positive, then it is called to the subcritical bifurcations. So these bifurcations comes to the scenario like this picture. A linear stability critical point. This point is the linear stability critical point. Beyond that, that point flow is going to be the unstable. The dotted line is the unstable, and two stable branches are there. Unstable branch is there. That is called to the subcritical bifurcation. And subcritical bifurcation is the most dangerous bifurcation in the fluid mechanics, because it shows that the flow at a linear stability analysis point, it is not a stable situations. At a linear stability critical point is not a stable situations. We need the further analysis for the bifurcation analysis. And basically the physical scenario of this is, suppose you have this ball here, then there is a disturbance implemented on this ball, then it reaches to here. It reaches to either here or either here. When it reaches to here, then it will downward. That is unstable situation. The situation will comes to the matching with respect to the original basic concept. In the subcritical bifurcations, a unstable point, linear stability critical point is bifurcated with respect to three different branches. One is the unstable branch, other one is the stable branch. So these stable branch is called to the supercritical. That means there is just a point where a nearby equilibrium state is exist. That means supercritical is give to the your linear stability results are reliable and give a equilibrium state. There is no sudden jump in the flow at that point, nearby that point. And that is, we can see, if you put the disturbance here, then this wall comes to here and it go to the stable situation. So basically this is a concept or analyzing concept with respect to the mathematics, how to develop the different type of the bifurcation analysis in a fluid mechanics problem. So my objective to explain here the basically one example, that ax dx by dt equal to ax minus bx cube. So how to calculate a bifurcation analysis? The same procedure we are going to implement for the Landau equations, and we develop the bifurcations analysis. So for any problems, we use to this concept and develop the bifurcation analysis for the any problems. So after use this theory, I show the some results. What is the major advantage and disadvantage of the linear stability theory? The picture one is calculated by the linear stability theory, just in with respect to the flow feature. The picture one is the calculated by the linear stability theory, and picture two is calculated by the weakly non-linear stability theory with the help of. There is a almost going to the similar, because I just want to say that this problem have only the supercritical bifurcation. I already declared the supercritical bifurcation is a very there is a no nearby equilibrium state is exists, so there will be no major change in the flow structure. So we can see here the problem contains the supercritical bifurcations, and here only the v velocity is slightly going to be changed. Otherwise, the cells are remains in similar positions. So that is one type of analysis. That for another parameter we have developed and see the several things. Then most of cases we found that supercritical bifurcations, and that bifurcations is matching with respect to the linear stability results. So that is the advantage to verify our results with the linear and non-linear and experimental, how things are going with respect to the linear instability mechanism and non-linear stability mechanism. Even though I have also examined for another problems to the subcritical bifurcations, and we have seen that in case of the subcritical bifurcations, flow is going to be give to the abrupt jump, like as a very distorted type of the cells. And even though the change in with respect to the linear to non-linear, we have examined what type of the cells are responsible or inside, then the second order cells are going to be this. They are going to be the destroyed the cells, and that's why the problems creating the some distorted type of phase from the one place to linear to non-linear. This you see the same parameter, same parameters, then flow is going to be this way. If this is linear case, this is non-linear case. Now this is, I have shown one particular type of problems is channel problems. Now I want to explain the some little bit idea of the more realistic problems in the geophysical fluids. Then you see that this is a most common problem in the geophysics, like as a problems is capturing like as a vortex dynamics. Vortex means cyclones we are seeing every times, and cyclones generating the vortices. Even though other planets we can see Jupiter the first type of this type of the red spot, and that is a large vortices, and that type of vortices we have to be analyze the fluid mechanics in these vortices. If vortices the pressure is inside in the vortices, that is going to be the anticyclone and not creating problems. When pressure is outside the vortices, then creating the cyclone type of structures, and it create the cyclone in the oceans. So how to develop the stability analysis for a vortices means my objective, yeah, any fluid mechanics objective, they have identified how much strength is required to distort a vortex in particular length or measurement. So according to that idea, we can preserve the things, or we can arrange the situation ki how much strength will give to the cyclone. Because if have an idea that this vortices is this size, then we know that how much pressure will be created and how much the vortices will create the strength in the cyclones. So one of the interesting things in the vortices, the density stratifications. Basically, density stratification is nothing but it is a just a density is decreasing with respect to the temperature layer. Suppose I just explained, this is not a big task. If you plot the density with respect to height, always when we will go to the density is decreasing with respect to the height, and this is called to the stable stratifications. This situation is called to the stable stratifications. If layers of the in the fluid mechanics, layers in the flow is available, so definitely the layers will going to be the arranged like a more dense flow is downward, then less dense flow is the upward directions, then is called to the stable stratifications. But sometimes we forcefully those factors are going to be added, then if density take them the reverse way, that definitely you directly go to the unfavorable situations. It is not possible that density is always decreasing with respect to height, but we take the suppose some forcing factor forcefully, the density is increases with respect to the height. That is called to the unstable stratifications. Stratifications words means representation of density in the layers actually. Stratification means representation. Either generally this is decreasing, that is called to the stable stratification in the vortices. So that vortex dynamics, because vortex is like this type of structure. Vortex means there is a region where the fluid particles are moving along the axis. That is called, when fluid particles rotating about the axis, that is called to the vortex. And there are several known vortex, and here I have given a one example of the Stewart vortices. And this vortex structure is like this, and it is a very special characteristic of this vortex that three different type of the streamlines are appearing in this vortex. One is the at the center part, that is closed. Other one is the some separatex types, and other one is the state line. And these vortex are periodic in that directions. This is periodic in that direction, but this is not a periodic in that direction. My objective to show this problem with respect to the stability analysis, because of this, how mathematics helps to us to analyze the things in the fluid mechanics. My basically main objective for this problems is how to analyze the things with respect to mathematics. Even this problems is very difficult to mathematics, a way of mathematics, but the same things is analyzed in mathematical way and matched with the experimental things. Those are doing the experiments with respect to the vortices. So basically, mathematics say that if something is periodic that direction, but that not directions. So if you use the basic concept of the Fourier series, then we sawtooth and another type of representation, then we make it the periodic. We take this type of structure same above, then we take the same structure above, then we will see after some time that it looks like periodic in the y directions also. So it will comes to the periodic in the y directions also. Then we make a 2-3 arrays, and then the structures are going to be the make with the help of the Fourier series, and apply the fast Fourier transformation to analyze for this basic flow. This is a basic flow for the Stewart vortices. Sorry, this is a basic flow, and this is completely two-dimensional basic flow, not one-dimensional. I put this main governing equation in the Navier-Stokes equations, then develop the same linear stability equation and apply the linear stability theory and develop few results also. So basically these results give to very nice information. You see here 3 different type of points are here. This go to this line. This is a looks like an elliptic structure. This is the hyperbolic structure in mathematics. So that point is called to the elliptic point, and that point is called to the hyperbolic point. And my arrangement is to make this problem in the periodic forms with the help of the Fourier series and Fourier transformation. Then after that, we can use the mathematical concept of the fast Fourier transformations and develop the periodic part in the y directions, and then solve the problems. And this see very nice structure at the center for a particular value of the floor number. Floor number is the denote the strength of the stratifications in the system. You just for maybe those are not getting the concept physics side, then you may attempt like as one parameter. Then we obtain there is a situations where this near at a center, this point. Sorry. This center, we see the situation is like that. When we increase this FH, then stratification is going to be increased. Then this is going to be the this to this, and this to this, and finally this to this. That means more perfect structure we have seen in this. That is called to the elliptic instability in the vortex dynamics. So a purely elliptic nature, and that nature is one of the dangerous instability in the fluid mechanics, which is observed in the for Stewart vortices. And it's calculated by me that that point is we have obtained the elliptic type of instability in the flow fields. So that is a very interesting way that is going to how to change slowly it is going to be stratification is going to be increased. I observe that how it is going to be changed. The vortex are going to be changed like such way, and finally we convert in the elliptic instability. So basically the whole talks is how do I summarize the things. We have how to analyze the instability property in the fluid mechanics. Basically, first we selection of the problems, and after selection of the problems, we have to be connect with the physics or real situations of the problem. And after real situations, we have to be apply the basic linear stability theory that we need through basic flow. Basic flow is nothing is not new things. Those are doing the flow analysis, the main governing equation and situations. Even those able to know in the theory of body, they know very well how to equations with respect to critical point, because in theory of body always basic flow we are not using the word the basic flow, we are using only the critical point. Here in the fluid mechanics we are using the word the basic flow, that critical point. So about the critical point, we have to be see scenario with respect to the nonlinear stability analysis. And in the fluid mechanics, it comes to the in terms of the Landau equations. It is nothing new, but is famous equations. But a solution, I have given a dx by dt equal to ax minus bx cube or plus bx cube. Then the supercritical and subcritical bifurcations. That bifurcations we can analyze with respect to the point at the linear stability, nearby the linear stability analysis. And linear stability analysis completely eigenvalue problems. So we have to be converting the eigenvalue problems and calculate the different modes in the stability analysis. And most unstable modes we have to be pick up and then check that the flow is stable or unstable. So this is a basically fundamental background of the stability analysis. And this is talk is prepared with respect to the main. I have taken the help of the basic book of the stability analysis, hydrodynamic stability analysis, Drazin and Reed. Even though the pictures, few pictures are taken online and few published work and few from my published work also. So thank you so much. If you have any doubt and query, then ask to me.
Yes, thank you so much, Manish. So now if anyone has any queries, so please ask that.
Good evening, sir.
Good evening.
Sir, I'm working on boundary layer flows of nanofluids.
Okay.
So, sir, if studying the boundary layer flows of nanofluid, we go by the rule you say we first model the flow with the help of the governing equations, and then we pick the physical problem. While we model the equation, so while we non-dimensionalize our equation to find the similarity solutions, so we obtain some non-dimensional parameters. So
Yes,
sometimes what
yes.
happens, so sometimes what happens is when we find the numerical solutions with the help of the non-dimensional parameters, if say with respect to some particular parameter that creates the instability into the system. So
Yes.
so suppose that parameter while we are studying gives solutions till the value equals to 1, but when we set the value of that parameter greater than 1, it sets the instability into the system. So does this give an idea about the so should we study the linear stability like you told, or when we do the analysis, so what should we do with that particular parameter with respect to the physical situation?
Yes. Now I just going to explain. In case of the boundary layer analysis, there are the two situations. Boundary layer is a very small case where we have
Yes, sir.
take care the flow is in viscid situations, and the velocity gradient is equal to zero and not equal to zero in the boundary part.
Oh,
Then
yes, yes.
basically we comes to the a simplified form of the differential equations, and second equation is going to the pressure derivative of pressure equal to zero, and first equation have some terms and remove some terms with the by order analysis. If
Yes, sir.
order analysis, if this term is less than one, then this term we have to be remove it because it will not going to affect in the boundary layer. But according to your questions, I feel that you are facing with respect to the numerical problem. This is not the flow stability or instability, first of them,
Hi,
because we
sir.
are using this is you are going to use the similarity transformations, then convert the partial differential equations in the ordinary differential equations. I think most of cases you are using the similarity transformation eta equal to root over some 2 pi something, this type of
Yes, sir. Yes, sir.
structure.
Yes, sir.
So that similarity transformation convert in ordinary. When we are solving the ordinary problems, that is called the numerical stability or instability problems. So now to overcome these problems, we have to become, suppose you have obtained some ordinary differential equations, you are going to just solve these equations by the finite difference in case, suppose. So finite difference equations is give a very slow convergence. So that is a problem with respect to the convergence. But this lecture will help to that problem to develop this. Once you developing this boundary layer equation, that is called to the basic flow. You convert all those system and ordinary differential equation, that is called to the basic flow. Now to apply the disturbance there, then you will get the linear disturbance equations. So one part you have done, but your basic flow is not going to solve because of the numerical problem still. So either is one thing is this, you change the solution method. Whatever methods you are going to approach, suppose you are using some Laplace transformation, maybe using the finite difference method, maybe using the finite element method. So this is a main problem in the fluid mechanics. Tackle a problem with respect to the numerical analysis. It is another different tough part, because numerical simulations need the several efforts.
Yes, sir.
Yeah. So
Okay,
I
thank
think
you.
both things
Thank
are
you.
clear. This
Yes, sir.
your instability comes due to the numerical, not the my procedural instability, not like that. If you're willing to go the linear stability of that problem, so you have to be, those are up to here you solve that problem, that is called to the basic flow. Now you apply the disturbance there, and you will develop the only stability equation and eigenvalue problems.
Okay, sir. And sir, one thing more, like in the slide 42 or 43, you had a table drawn where you have the different values of the parameters taken around 42 and 43.
42 and 43. Yes.
Sir, this one.
Hmm.
So, sir, like also you said the value of the Prandtl number for water is 7 and the air is 0.7. So while you change these values, sometimes the problem is faced that we have to take the values according to the situation that the problem is physically true. So any upside value will not do any good with the analysis. So with the non-dimensional parameters, sometimes like the Prandtl number, they are fixed for particular fluids, and Reynolds number we decide for the turbulent and laminar flow. So for other parameters, so how do we decide that while we are doing our analysis, so what is the range of the values we should be taking for our analysis?
Yeah, very nice questions for those who are doing the fluid mechanics, because the all fluid mechanics is play a very important role to choose the value of the governing parameters. So basically, when you are doing the numerical simulations, we have a freedom. Freedom means we have choose the any value of the parameters first of all, but it doesn't mean that we can choose any value, because every value give to the physical scenario. Like if you are choosing the Prandtl number 0.7, then you are talking about the system with respect to the air. If you're choosing the Prandtl number 7, you are talking about with respect to the water. If you're choosing the Prandtl number 100, that means you are talking about the system with respect to the heavy oils. Then that facility is available on the numerical simulations. But you are going to conduct an experiment, is very difficult to change the different fluids in the every time. First of all. Second things, before analyzing the problems, we need a concern about the parameter, what does it represent. Suppose you increasing the Reynolds number. Physically think it, Reynolds number is going to be increased. That means what things is going to be increased? That is only the velocity.
Yes.
Is it clear? If
Yes, yes.
you are going to be increase the velocity, so which we use the common sense. It is going to be stable situation or unstable situations. Because when you are going to open a tab, then tab is just a open, then you see the flow is going very smoothly. Then increase the strength, that is called your Reynolds number. If you increase the strength in the tab, then your flow is going to the arbitrary path. So these physical situations you have to be connect with respect to the mathematical definition of the parameter. You see the Prandtl number is mu by alpha. Mu is the kinematic viscosity, alpha is the thermal diffusivity. Then think about the kinetic viscosity and thermal diffusivity same time. Then you automatically click that we have to choose this. Even though I want to say that several nano fluids person, those are doing the nano fluid analysis, and they have used to the nanoparticle in the in the conventional fluid. And I asked to the several times what type of the conventional fluids you have taken. And several I have seen the papers, they have taken the Prandtl number is 2, 5, 7, something, any arbitrary value. They are saying that we have taken the PR equal to this. If you are taking the PR equal to 2 and adding the nanoparticles, is it possible?
Yes, sir. The problem, I've also seen this in many papers, because
Many
people
people,
use.
it is possible if you conventional fluids say, if I will say that I have taken a water and I have incorporated the Al2O3 nanoparticle, it is feasible. It is possible that experimental persons can take a water, then put the Al2O3 nanoparticle and conduct a new experiment with respect to this nanofluids. Kerosene, base fluids, they can take it. Ethanol, they can take it. But PR equal to 10, PR equal to, either they have to be explained, if PR equal to 10, this type of fluids we have taken for a develop a nanofluids. But if you are writing a paper of nanofluids, you are not declaring the conventional fluids, then it is totally paper in without physics. At least those are doing the nano. Even I am also working in the sometimes nanofluids. So first we have to be clear that what type of the conventional fluids I have taken and what type of the nanoparticles we are going to be add there. So that type of the nanofluids comes to output. And you can ask to the chemistry person, they will completely declare that properties of that nanofluids and you will match your results. Definitely it will match. Even it is my own practice. I have done this type of job. I have taken a water and add the Al2O3, titanium oxide and copper oxide, 3 different type of nanofluids, and analyze the numerically and ask to the chemistry person which one is the more stable. Then he told me this one is the more stable. I told them my graph is saying same things. So before that is very important, even though nobody is talk to you because this is a numerical code, whatever value you will give it, the code will give to the graph you. But once you go after coming the outputs, you have to need to analyze the things. Any other question?
Okay.
Nice
Thank
question,
you, sir.
but this one is a very interesting question. To choose a parameter is very difficult task.
Okay. Thank you, sir.
Okay,
Thank you.
so
Any
now
other?
Manish, in chatting box, you have one query there.
Yeah, one is this is the which normalization technique is used if value of S large. Actually, I'm not getting
Value
if
is
explain
large.
the
Large, large.
Which normalization technique is good if value is large?
not is S is not na?
I think so.
Value is
Not.
large.
Yes, it should not be, sir.
Okay, okay. So are you talking about the normalization is the non-dimensionalized in fluid mechanics or normal mode analysis? Generally, we use to the pi-Buckingham theorems to normalize the parameters. And there are the several combinations possible with respect to the pi-Buckingham theorems. Then according to the situations, we use to the non-dimensionalize the parameters. Generally, I use to the pi-Buckingham theorem. Even though one more theorem is available, but right now I don't know the statement of that theorem. But pi-Buckingham theorems give to the several combinations and for the to non-dimensionalize and normalize the parameters to free from the dimensions. So in that case, I am using the just pi-Buckingham and that combination suitable for my problem that I choose it. But it give not like a unique. It give to the several combinations based on your dimension of the and parameters and considered in the problem.